What's going on, physics students? Today we're going to basically be doing a whole bunch of example problems to try to see if we can get this thing through. I'm going to just record a bunch of these things and hopefully you'll get this. Then after that, I want to go over a concept with you, and it's called trigonometry and doing two-dimensional motion and that kind of stuff. We're going to need those tools to basically be doing our lab next week. And so today's going to be kind of an awesome day. All right, let's try this one out. Ready? Let's read, turn the page before that. Let's try this one, catching a speeder.
Okay,
Read it out loud.
A speeder doing 40 miles an hour.
All right.
How about
So we got, how, and then this.
A speeder doing 40 miles an hour.
So this guy is doing 40 miles an hour. Got it.
In a 25-mile-per-hour zone, approaches a parked police car. The instant the speeder passes the police car, the police begin their pursuit. If the speeder maintains a constant velocity and the police car accelerates with a constant acceleration of 4.51 meters a second, the first question is, how long does it take for the police car to catch a speeder? How far?
Wait, you're talking too fast. No. This guy's moving at a constant 40 miles per hour, right?
Yes.
This guy
Stopped.
starts off at, so this is V initial.
Yes.
And then this guy's V initial is 0. But his acceleration is what?
His acceleration is 4.51 meters a second.
Alright, so his acceleration is 4.51 meters per second.
But it's the textbook also gives 40. The textbook also gives 40 miles an hour at 17.9 meters a second.
Alright, let's go with that.
Let's just erase 17.9 meters a second instead.
Yeah, I'd rather do all the same units. So 17.9. Okay?
Alright then.
Now what? What is it?
How long does it take for the police car to catch the speeder? How far have the two cars traveled? And what is the velocity of the police car when it catches the speeder?
Alright, so this is where the car is, right? And this right here is where the police car is. So this would be the speeder and this would be the police car.
Alright.
And then, like 1 second later, the speeder is going to be way out here, right?
Okay.
The police car is only going to be maybe about here. Do you agree? Because this guy's going way faster than this guy's going. This guy's just starting to go. He's going to be going 1 second later. He's going to be going 4.51 meters per second, whereas this guy's already going 17.
So, wait, can we set up a ratio to find out how many miles he's going?
Well, here I'll show you the probably the easiest way to go about this. And then before we start this, I want to write down these two equations. It would be V final equals V initial plus AT, and then delta X equals V naught T plus 1/2 AT squared, and delta X equals V final plus V initial all over 2 times T, and V final squared equals V initial squared plus 2A delta X. Do me a favor and go to the side just real quickly. Okay, these are the 4 equations. Take a snapshot of that. Not just you can stand in front of them so you can see. Alright. So those are the 4 equations that I need. And alright, and your job also is to put it at one hand up here so it doesn't fall.
Doesn't seem to be falling. It seems to actually.
Yeah, it's just balancing. I don't want it to.
It's leaning actually
Alright.
on the desk over there.
So these are the 4 equations that I'm going to use. I'll probably be coming back to this often. Now, at some point in time, the speeder is going to be way out here, but the policeman's going to catch him, so that implies
That he'll speed up.
Well, right, he is speeding up. He's speeding up with an acceleration of 4.51 seconds
All right.
per second squared. But what I'm saying is, at some point, the policeman is going to be out here as well. Because if the policeman is ever going to catch the speeder, he's going to need to be at the same position of him. Does that make sense?
Yep, that makes sense.
All right. Anyway, let's apply some equations to this guy right here. By the way, what is the speeder's acceleration? This right here?
No, wait, that's the speed.
That's the velocity he's moving at.
You wanted to know the acceleration. You'd have to know what speed he was initially going. if he was going any speed.
Well, it tells you in the problem. It says he maintains a constant velocity of 17.9 meters per second.
Okay, so then from that we could.
So what is his acceleration?
His acceleration would be 0 because his velocity isn't changing.
Exactly. The word constant velocity means
Acceleration is automatically 0.
it's
Write
no
that
acceleration. All right,
Write that
fine.
down.
Here, you write it down.
Okay.
Here, write it a little bit lower, because remember, that's what the computer says. So you want to remember that constant velocity means a equals 0. All right, cool. So, what's an equation I can apply to him? Let's see. Let's deal with.
What we've
Wait, what was the first question? Where do they catch? Where does the policeman catch? That was the first question, right?
How long does it take for the police car to
Okay,
catch
so
the
we're
speeder?
looking for time.
So we would use.
So I told you there's 5 different equations. Let's see if this thing helps out. It just makes the whole thing hotter. No,
turn it around. Turn it.
No, I don't want to shine it straight into the thing. All right.
Does this one have power?
So there's 5 different equations to use. Or there's 5 different variables to deal with. You turn the back.
Oh, there we go.
But shine it against the wall, so the wall's.
So the wall reflects the light.
Yeah. Alright, so there's 5 different variables that you would be using. The 5 would be V initial, V final, acceleration, time, and delta x. Cool? Now we're looking for time, so that's our question mark right there. Cool? We have the V final, or we have the V initial of this car, right? What is the V initial? 17.9. Good. What's the V final?
The V final is
17.9.
it
for this.
never changes. So ideally we need an equation that has only one instance of V of 0.
And I just realized that, you know what? There's going to be something that comes into play here. What is our acceleration of this first car?
It's non-existent.
It's 0, okay? And what is our delta x?
Okay, that motion over a straight line.
Well, it would be this distance right here. The distance that this car traveled until he got caught.
17.9 meters a second.
Well, we don't know how long it took.
We don't know how far he went, and we don't know how far.
So I'm just going to leave that as delta x.
Because we don't know what delta x is.
Yeah. But I'm going to show you something that's really cool.
The V.
All right. Now let's apply this same idea to the policeman. So the policeman, do we know his V initial?
It's non-existent.
It's 0. Do we know his acceleration?
It's 4.51 meters a second.
Okay, do we know the time?
We don't, and
No.
we don't know the x either.
And the delta x we're still looking for. But
no, wait. The delta x of the policeman and the delta x of the person that is traveling would ideally be the policeman's one is half of the policeman's one is half of the speeders, because it says the second that the policeman is passed by the speeders, the policeman notices and starts driving to catch up.
I don't think it's half, but I think you're on to something.
It's
You're right.
some
You're
fraction.
right in that we don't know what the delta x here is. We don't know what the delta x there
But
is.
there is a ratio between the two.
Yes, it is a ratio. In fact, it's the ratio of 1.
1 to 1.
It's a 1-to-1 ratio. When they catch each other, and this is actually kind of a physics intuition thing I want you to get. What can I say about, I don't know what delta x is true, but what can I say about delta x for the speeder and the police car the instant that the police car catches him?
Both of their speeds become 0. Their velocity in this case, the velocity becomes 0 in both cases.
We're talking about this guy doesn't even slow down. This guy turns on his lights, this guy doesn't even slow down. He maintains a constant velocity of 17.9. But when the police car catches him, their speeds aren't 0. The police car is moving, this guy's moving. But I'm saying, when does the police car come into the same line as him? I can tell you that this delta x is the same.
Okay, then, so...
Does that make sense? Like, the distance that he traveled.
Okay, so just make sure they know they're equal.
Alright, you can't see that with that marker.
Dang it. Okay, just write it in
Go
more.
inside this drawer over here.
I'm going to be walking in front of the camera for a couple of seconds.
That's fine. Grab the purple. Purple should. Or there's another black.
Yeah, I'll use the purple one so that they can distinguish who's writing on the board.
Okay. Alright.
So both of these quantities are equal.
When the speeder catches the guy. At catch. Just put catch. Alright,
Which
so,
is the
so these guys are equal at catch. Okay? Now, here's the thing. I don't have what variable do I not have? I have the initial, I have acceleration, I have time, I have delta x. Even though technically I don't really have the value of delta x, there's some important information about it.
They are both the same at the instant that the policeman
Right.
catches up because they both stop.
Well, no, they don't stop. But
They both travel the roughly equivalent distance.
yes, they travel the equivalent distance. That's true. Okay, but which variable do I not have? V final. Okay, so then what you do?
Either one of them.
So then what you do is you take a look at these four equations. So you move to the side just so people can see the four equations. Take a look at these four equations and you ask yourself, well, which one of these four equations doesn't have V final in it? Because I don't want to use an equation here
for a number that I don't have.
for if it involves a number I don't have. So which one of these four?
Does not involve V final.
Yes.
Well, actually, the only one that involves V final is this one, the wall over 2.
Well, here, move to the side so we can see. There we go. So the V final, you're saying this V final right here?
Yeah, that's the only equation that involves V final. Okay.
I see one right there.
Then this one right here.
I see one right there. So it's the second one. Or I guess I wrote it out of order. Usually I write this as the third one. I think I switched these on accident.
So we're
but
going-
anyway, it's the one that goes delta x equals v naught t plus 1/2 at squared. Cool? So let's apply this equation to the car. Delta x equals v naught t. So v naught, I'm going to put a v naught with a little s on the bottom. Do you understand why that's a v naught s?
That's the speeder. We're just using
That's the velocity initial of the speeder. Exactly. Times the time plus
half of the
1/2
of the acceleration.
AS t squared.
of the
But AS is what?
acceleration of the speeder. You should have just said A sub s.
I did. A sub s.
Okay, thank you.
A sub s is what?
It's the acceleration of the speeder.
And what is it?
The acceleration? You can just write this as 0.
Good. I want some more room, so just cross out that entire term because when you multiply everything by 0, no, everything in there. The 1/2, the t squared, it doesn't matter what those are. That whole thing 0, right?
So basically, all we're going to use is this portion right here.
Perfect. Alright, so check this out. Now, let's apply this same equation to the cop. Delta x equals v naught policeman times time plus 1/2 a policeman times time squared.
So what numbers do we know for the policeman? It turns out that the equation will entirely work because the only number we know for certain is the acceleration.
Well, you don't know. You know the velocity initial.
But it won't work because it'll cancel out this entire term.
Sure. What's wrong with that?
Okay.
Alright, now,
Then we plug in 4.51.
sure, we can plug in that. But before we do numbers, I know that you're big on numbers. I'm not a big fan. There's one other important piece of information that we need to use at this point to solve out for t. We have two equations, right? 1, 2. We have two things we don't know, delta x and t. We know this. We know this. We don't know t and we don't know delta x. We have two equations, two unknowns. And I've told you once in the past, anytime you have two equations, two unknowns, you can solve this problem.
Okay.
Because there's one piece of information that I know for sure. That what?
That their final velocity will be equal to each other.
I don't have any final velocity anywhere in this equation. I don't see a VF anywhere, so I'm going to stay away from the word final velocity here.
These equations have missing halves that roughly equal each other. See, the first half is missing in the second one, and the second half is missing in the first one.
No.
That doesn't have any significance? I thought it might.
I'll give you a hint.
the delta x or their position graphed on an x scale is equal when the speeder gets caught.
Exactly. So
whatever their velocities are.
So I can equate these two basically, because this is delta x, this is delta x. I know that those are equal to each other.
So we can put
right here. I'll tell you what. Why don't you take it from here?
So, oops! I said on something. I said on the cord. I said on this cord. Just turn it on.
Okay.
Oh wait.
That's all right. There's not a whole lot of room.
Okay, so
Actually, you know what? I'm sorry. Why don't you work right over here and work small?
Okay.
Just because there's not a whole lot of room at this point.
Is equal to 1/2 Now can't we solve for t by using square roots?
Sure.
So we find that, so as soon as we, so we do know at least one of the numbers for this one.
So basically you said this thing equal to that thing.
That's what you told me to do.
That's what I think you should do.
Okay, so 17.9 gets plugged into the velocity.
Wait. You don't plug in numbers yet. Just get t all by itself.
Okay, then pass me the top. You really should wash this thing. It's getting dirty. Alright, then. Yep, guys, we're doing square roots. Shouldn't be that much more. So,
Actually, before you do the square root, what I'd rather you do,
okay, what do you think I should do?
I want you to get t all by itself.
I am trying to.
Okay, all right, fine.
That's part of it. That's part of me getting.
Well, first of all, can you write exactly what you have up there on the line below? Because you can't see it.
Okay.
So V naught S.
V naught S T.
Yeah, get rid of that square root. I'm going to teach you. I'm going to make you do something before you do the square root. Here. In fact, get rid of those 4 equations.
These ones?
Yeah.
Hope you guys got these down.
That's all right. I got them memorized. I can pull them out for you anytime.
Alright. Here we go.
All right.
Now, hold on. I need to get rid of the square root too, because you said to get rid of that.
Yeah. And get rid. Oh, okay. And that's equal to.
Then get rid of the top equation that can only be seen by the webcam halfway. So 1/2 a of p times t squared.
Perfect. Get rid of the top equation.
It was wrong anyway.
No, it wasn't wrong. It was perfect. In fact, taking the square root wouldn't have been wrong either.
Then why'd you tell me it was wrong?
Here, move to the side so people can see. All right. So keep in mind, you don't want to put your face right in front of the thing because you can't see your face all.
You better not be pulling.
Right.
You better be pulling a Mr. Miyagi. Please don't do it.
I'm not pulling a Mr. Miyagi. You think I'm going to teach you to wax on, wax off this thing? No.
No. It's a metaphor. It's teaching me something completely different that somehow relates to this.
It's not completely different. What I'm just saying is, look, there's 1 t here, there's 2 t's here.
Alright.
How do I get rid of that t?
I can't think of any way to do
How
it.
could I put that t onto that side?
You subtract it out of itself.
You can't subtract these things. These things being multiplied by this v naught s.
Although you divide
Alright, you divide by t.
divide both sides by t.
Good.
And you're left with v naught of the speeder.
Don't put a line through that because that looks like an angle, which we use angles as well. Move the side, remember?
V naught of the speeder is equal to
Yeah.
1/2 AP. Would the t still be there?
Yeah, wait, just a little p. Make sure you're very careful with how you write it.
Is the t still going to be there?
Well,
Because we're
ask
taking
yourself this: there's 2 t's on top.
No, there's technically not. It's t times itself.
Okay, there's 2 t's. There's
Okay, so
t times t.
So we're just left with another t.
So you're left with just 1 t. And now look. At this point, you don't need to take any square roots.
You don't. As soon as you know what time it is.
To the side. I love you, man, but you keep forgetting that. Yeah, you don't need to take any square roots. You just need to get t all by itself at this point.
Okay.
Does that make sense? So let's get rid of that 1/2.
Okay. How do we get? We just erase it.
Oh no, you can't just erase it. That's not being fair, dude.
Multiply both sides by 2.
Multiply both sides by 2. All right.
2v naught of the speeder equals 1
Well, you
We're
don't need
gonna
to
we're gonna write it there anyway.
Okay.
I used to make that mistake too, and who's to say there are kids in your class who probably still make the same mistake?
Well, I'll tell you one mistake you make.
The T should still be there should be a 2 in front of the T.
Now you should move to the side so people can see it. All right.
This is by the way times by 2. I wrote the 2 up there by accident.
Yeah, it's not squared. I get it. Get rid of the AP. And I'm going to get rid of this one.
Okay, what do I do to get rid of the AP?
Well, what is AP doing to the T?
It's multiplying.
So how do you get rid of AP?
Divide both sides by AP.
There we go.
I'm about willing to accept your crazy physics formulas.
It's not crazy. All right, cross out those APs. And do me a favor again. Write that. I know you're going to be like, why is Mr. Baldy being such a stickler on this? Write that P small.
Because P can
And stand to the side.
Because P is used to probably represent something completely different, like
No. It's just because P is a subscript over here. It's just telling me that's the police officer. I don't want to think of P as a separate variable. And when I see A with a P next to it, I'm thinking A times P.
A sub P.
Yeah, A sub P. That's
So
all.
now that we know about this, we can we divide everything by 2 again or no?
Why? We got T all by itself. It's solved.
So this is the approximate ratio that we
So that's the answer. I mean, you could plug in numbers if you want. You
but
could
we
plug
don't.
in.
It was asking for exact numbers, not conjecture and theoretical.
Well, no, but that's what I'm saying. At this point, you're almost done. I got a T here. Stand to the side. All right. At this point, I'm almost done. I've got a T here. Why is this not working?
I'm
Big
working on,
spoil. I've got a T here. All right.
it's not working because I wrote it there.
T is equal to 2 times velocity initial of the speeder divided by the acceleration of the police officer. Yeah, that's it. Now, you can plug in numbers and go for it, by all means. Pull out a calculator, whip it out, and plug in numbers. Do you have a calculator?
I have my Chromebook.
Go grab it.
Hold this, please.
Okay.
I'll bring it.
All right. Now, while you're grabbing that, I want to show you one thing real quick. And that's this. We have 2 times the velocity initial divided by AP, and that's equal to T. This is what we're saying our answer is. One of the best checks that we can do as students, as math-based students, is we can check to see whether or not this is correct
Right.
as far as units go.
Okay.
Do you understand what I'm saying here, Justin?
Yep.
All right.
Move
So-
over, please.
So what I'm
I've got my
saying,
calculator app open,
so what I'm saying here is we need to check to see whether or not this is actually. You know what? Let's plug in your numbers first.
Okay.
Look at this.
What were the numbers that you wanted me to put in?
2 times
2 times.
velocity initial of the speeder.
I can't do these kinds of formulas. It's gonna say V is undefined.
No. You don't need. I'm telling you. I'm reading it straight off here. You should tell me. Oh, it's 17.9.
Okay, so
I mean, I have it written up on the board right here.
17.9
Divided by.
divided by the acceleration of the police, which is 4.51. Okay, is that okay? And that's the
Answer.
My computer says 7.937.
7.937.
Yeah, go, Mr. Dalday. There's probably like a section in the back that gives the answers.
I think the answer's right there.
17.
No. It's the next page.
Okay.
That's for the previous one.
Okay, let's go to the next page. Let's see here. Technically speaking, I must have done something wrong because, okay, actually yes, they did get 7.94. Okay, Mr. Dalday, write 7.94 down, and we're going to put that into the equations for calculating the forward motion of the individual people.
Wait. But did they get exactly what you got? What did you get?
Yeah, I actually got a more exact number than they got because they rounded theirs, but my calculator does stuff out to the 12th decimal.
Sure. All right, but that's what I was telling you about significant figures.
When you're working with most physics equations, two significant figures are all you need.
No, that's not it either. What I'm saying, like, for what an answer to your question is, the velocities and the acceleration that they gave us, how many significant figures were there in those equations? Justin.
Okay, I heard you.
How many significant figures were in those equations?
There were only one in one of them and two in the other one of them. So
No. There's 3 here, and there's 3 sig figs here.
Okay, that's completely different because 90% of the dictionaries I looked at said that it was every number after the decimal point.
No. But the numbers before the decimal point count as well. The non-zero numbers before the decimal point count as well.
All right.
You need to learn significant figures. Anyway, there's 3 sig figs here, there's 3 sig figs here, so we should round our answer off to 3 sig figs. Would you agree that that's correct?
Yes.
All right. Can I show you one more thing?
Yeah, okay. I don't know enough physics to disagree with you.
Well, I mean, but at least we got the same answer
Okay.
without rounding it, right?
Yep.
Okay. All right. Can I show you one more thing?
We need one more. There's one more equation.
I know. But before I finish this, I want to show you one.
All right.
Because what I'm showing you here now is not how to solve it as fast as possible. I'm trying to show you the technique of solving it.
Okay. So
All right. Move to the side.
I'm going to need to actually move out of the range of the webcam so the students can see whatever
No,
formula.
I'm just going to do it down here.
All right then.
You can stand right there. Stand right there where you're standing. Awesome. All right. Here's what I'm saying. We got an answer. Apparently, we got the right answer. We know for a fact that it's the right answer because we checked the book.
Yep.
Right?
Book says that.
Right. But I can actually say that once I get this answer, there's a quick check that I can do. And I want you guys to think about these checks and do these checks. Because it's probably one of the best things that help me out. This is the answer I got. What I want to do is I'm going to check just the units. I'm going to do it in the color black. Okay?
It gets plugged back into the original
No,
formula.
I'm not going to do that.
Okay, that's a common one. I know that from algebra.
Well, here's what I'm going to do. Okay, back up a little bit. Okay. What is the units of the number 2?
Seconds. Wait,
2 seconds?
2 doesn't have any units.
No units. Good. So we're just looking at units here.
Velocity has
What is units of velocity?
Velocity has meters a second,
Meters per second.
which is not a unit. It's a rate.
What is the units of acceleration?
Same thing.
Meters per second?
They're both meters per second, and it ended up
No.
in seconds.
No. Acceleration is meters per second squared,
So
right?
So
'Cause that's what
technically
they use.
speaking, it makes perfect mathematical sense why we got seconds for the answer.
Why?
Because the two opposing meters cancel themselves
All
out.
right. So the meters cancel out with the meters.
And the second squared cancels out half of itself, leaving this second.
So this second cancels out with that second squared. So there's only 1 second over here. Well, wait. But that doesn't give me seconds. That gives me seconds in the denominator of the fraction that's on the bottom.
So technically speaking, we've done something wrong, even though we've done.
No, it hasn't. No, it doesn't. Isn't. Because I've got a fraction divided by a fraction.
Which just results in that. Which just results in s. Obviously.
Right, because when you take a fraction on the bottom, the way you deal with this, you take the fraction on the bottom, you flip them over, right?
Which makes it into a whole number.
So it makes it s over 1.
Yep.
Now, you can easily see that this is equal to seconds. Correct units. If we have the correct units, I would venture to argue that we are probably on the right track if we have this answer.
Oh, okay.
I mean, that's what I'm saying, is you have a way to check your answer. You take your answer, you get whatever answer it is. This is why you were so eager to plug in numbers, and I was saying, back off, don't plug in the numbers yet. Because if you don't plug in the numbers, you'll get an equation like this. If you get an equation like this, you can check the units. You can't do that if you plug in numbers too early. Engineers always do that. I took an engineering class over the summer, and as soon as the teacher assigned something, they went, whoosh, and they took out their calculators and they're trying to calculator it up. Don't do that. I mean, try to get it this way and then check the units. If the units work out, then guarantee that that's the correct answer.
Regardless of how silly or stupid
Well,
the number is.
Almost guaranteed that's the correct answer. You could be missing a 2 or drop that.
There's
or
no
that stuff.
accounting for human stupidity. Even
Well-
Mr. Dalday still makes mistakes.
Yeah,
sometimes.
yeah. People make mistakes, but I'm just saying that like it's a good sign if your units match up. Because if you solve it out and your units don't match up, then I can guarantee you that your answer is not
If
correct.
your units match up, there's a significantly higher possibility, though not 100%, if you will, that the answer might be correct.
Yeah, I'm cool with that. Does that make you happy?
Don't write that down. I talked a little too much.
Anyway,